There is an object, right now, moving through space beyond the edge of our solar system. It is smaller than a car. It was built by human hands in the 1970s. And it is still out there, still sending signals back across a distance so vast that those signals, traveling at the speed of light, take more than 22 hours to reach us. Tonight, we are going to follow Voyager. We will trace its path from launch to the outer planets, through the boundary regions of our solar system, and into the space between the stars. We will look at what it found along the way, what that data revealed about the edges of our sun's influence, and what it means that something made by people on Earth now drifts through interstellar space. This is a long, slow journey. We will take our time with it. Get comfortable, and let's begin. At Sleepy Time Universe, we explore the science of space slowly and without hurry, for curious minds that need a place to rest. Chapter 1. Born in a Moment of Ambition. In the mid-1970s, a small group of engineers and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, were working against a deadline that would not come again for another century and a half. A rare alignment of the outer planets was approaching. Jupiter, Saturn, Uranus, and Neptune would be positioned in a configuration that would allow a single spacecraft, using the gravity of each planet in turn, to visit all four in a single continuous journey. This alignment would not repeat until the 2150s. If NASA wanted to take advantage of it, they had to launch in 1977. The mission that emerged from that urgency was called the Voyager program. 2 spacecraft would be built, nearly identical in design, and launched weeks apart on slightly different trajectories. Voyager 2 launched first, on August 20th, 1977. Voyager 1 followed on September 5th, 1977, on a faster path that would allow it to reach Jupiter and Saturn ahead of its twin, despite launching later. Each spacecraft was built around a 10-sided aluminum frame. A large dish antenna, nearly 4 meters across, dominated the structure. This antenna would remain pointed toward Earth throughout the mission, sending and receiving signals across distances that would grow over the decades to almost incomprehensible scales. Extending from the main body were booms carrying scientific instruments, magnetometers to measure magnetic fields, plasma detectors, cosmic ray sensors, and cameras capable of capturing images of planetary surfaces and moons in more detail than anything achieved before. The spacecraft were also carrying something else. Attached to each one was a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to represent life and culture on Earth. There were greetings in 55 languages, music from many traditions, and natural sounds including thunder, wind, surf, and the calls of birds and whales. There were images encoding information about human anatomy, mathematics, and the location of our solar system in the galaxy. The records were not primarily scientific instruments. They were something closer to a message in a bottle, sent outward on the longest possible journey, addressed to whoever or whatever might one day find them. The decision to include the records reflected something honest about how the people behind Voyager understood the mission. They knew that both spacecraft, once past the outer planets, would continue traveling indefinitely. They would not stop. They would not return. Barring some collision in the deep future, they would drift through the galaxy for billions of years. In that context, the golden records were a quiet acknowledgement that this was not just a scientific mission. It was also, in some small way, a statement of existence. The scientific objectives, however, were concrete and demanding. The primary goal was to conduct detailed surveys of Jupiter and Saturn, their moons, and their ring systems. Voyager 2 would go on to visit Uranus and Neptune as well, making it the only spacecraft to have visited all 4 outer planets. The data returned from these encounters would reshape planetary science entirely. But in 1977, all of that still lay ahead. What existed in that moment was 2 spacecraft on launch pads, a narrow window of opportunity, and a team of people who understood that what they were setting in motion would outlast all of them. Chapter 2. The Grand Tour. The first destination was Jupiter. Voyager 1 reached the giant planet in March of 1979, and what it sent back surprised nearly everyone. Scientists had expected to refine their existing models of Jupiter. What they got instead was a series of discoveries that made clear how little they had actually known. The Great Red Spot, a storm system that had been observed from Earth for centuries, was revealed in extraordinary detail. It was not simply a large atmospheric disturbance. It was a complex rotating system with internal structure, with cloud layers at different altitudes moving at different speeds, with lightning flickering deep within it. The sheer scale of it was difficult to absorb. The storm was larger than the entire Earth, and it had been turning continuously for at least as long as humans had been watching the sky with telescopes. But it was Jupiter's moons that produced the most unexpected findings. Io, the innermost of the 4 large Galilean moons, was found to be the most volcanically active body in the solar system. Voyager 1's cameras captured an eruption in progress, a plume of material rising hundreds of kilometers above the surface. This was the first time active volcanism had been observed anywhere other than Earth. The heat driving those eruptions came not from radioactive decay in Io's interior, as it does on Earth, but from tidal forces. Jupiter's immense gravity, combined with the gravitational influence of the other large moons, continuously flexes and squeezes Io's interior, generating enormous amounts of heat. Europa, the next moon outward, told a quieter but equally significant story. Its surface was smooth and bright, covered in a crisscrossing network of lines and fractures. The leading interpretation was that beneath the surface ice lay a global ocean of liquid water, kept from freezing by the same tidal heating that made Io volcanic. The implications were considerable. If Europa harbored a liquid ocean, it also harbored the basic conditions that, on Earth, have proven sufficient for life to emerge. Voyager did not answer that question. It simply raised it, clearly and unmistakably, and left it for future missions to pursue. Ganymede and Callisto, the 2 outermost Galilean moons, were geologically older and more scarred, their surfaces preserving records of ancient impacts in a way that the more active inner moons did not. Each moon was a world unto itself, with its own history, its own surface chemistry, its own relationship to the enormous planet it orbited. Voyager 1 then continued to Saturn, arriving in November of 1980. Saturn's rings, always beautiful when seen from Earth, became something else entirely under Voyager's cameras. What had appeared from a distance as a few broad bands resolved into thousands of individual ringlets, some sharp-edged, some braided, some with gaps maintained by the gravitational influence of small moons embedded within them. The complexity was far beyond what existing models had predicted. The rings were not a simple structure. They were a dynamic system, constantly evolving, shaped by forces that scientists were only beginning to understand. Saturn's moon Titan presented a different kind of mystery. Titan was known to have an atmosphere, unusual for a moon. Voyager 1's trajectory was designed to pass close to Titan specifically, to study that atmosphere in detail. What the instruments found was a thick, opaque haze of nitrogen and organic compounds that completely obscured the surface. The atmosphere was denser than Earth's. The chemistry occurring within it was complex. The surface itself would remain hidden until the Cassini mission arrived decades later and deployed the Huygens probe directly into Titan's skies in 2005. After its Saturn encounter, Voyager 1's trajectory carried it upward out of the plane of the solar system. Its planetary encounters were complete. From that point forward, its journey would be outward and uninterrupted toward regions no spacecraft had ever reached. Voyager 2, meanwhile, continued on its own path, reaching Saturn in August of 1981, before heading toward Uranus and Neptune, completing the grand tour that the planetary alignment had made possible. Uranus, encountered by Voyager 2 in January of 1986, proved to be a world of subtle strangeness. It rotates on its side, its axis tilted at nearly 90 degrees relative to its orbit, so that its poles experience decades of continuous sunlight, followed by decades of darkness. Its rings were narrow and dark, quite different from Saturn's broad and bright system. Its moons showed evidence of geological activity, particularly Miranda, a small moon with one of the most varied and puzzling terrains in the solar system. Ancient cratered plains sitting alongside dramatically younger features, as if the moon had been disrupted and reassembled at some point in its history. Neptune, the final planetary destination, was reached in August of 1989. It was the most distant planet encounter in the history of space exploration, and it did not disappoint. Neptune had a storm system of its own, a dark oval feature that scientists named the Great Dark Spot, roughly analogous in scale and position to Jupiter's Great Red Spot. Its moon Triton orbited in the wrong direction, retrograde relative to Neptune's rotation, strongly suggesting it was a captured object rather than one that formed alongside the planet. Triton's surface had geysers erupting from it, driven by the sublimation of nitrogen ice warmed by the distant sun. It was cold and strange and beautiful, and it was the last world Voyager 2 would encounter at close range. With Neptune behind it, Voyager 2 joined Voyager 1 on the long outward journey. The planetary chapter of the mission was over. What lay ahead was something different entirely. Chapter 3. Beyond the Planets. After Neptune, the solar system does not simply end. It thins. The density of material decreases gradually. The sun's light grows fainter with each passing year, and the environment becomes quieter in ways that instruments can measure, but that are difficult to translate into ordinary experience. Both Voyager spacecraft were now moving through this thinning outer region, and they would continue moving through it for decades before reaching anything that could meaningfully be called a boundary. The region beyond Neptune is not empty. It contains a broad belt of icy objects, remnants from the formation of the solar system, orbiting the Sun in a flattened disk that extends from roughly 30 to 50 astronomical units from the Sun. This is the Kuiper Belt, named after the Dutch-American astronomer Gerard Kuiper, who in 1951 suggested that such a population of objects might exist beyond Neptune. The belt was not confirmed observationally until 1992, when the first Kuiper Belt object beyond Pluto was detected. Since then, thousands have been catalogued, ranging in size from small rocky fragments to objects large enough to be classified as dwarf planets, with Pluto itself being among the largest known members. The Voyager spacecraft did not travel through the densest part of the Kuiper Belt. Their trajectories carried them at angles that avoided the main concentration of objects. But they were passing through a region where the solar system's ancient building material still drifted in cold orbits, largely unchanged since the planets formed some 4.5 billion years ago. These objects are preserved in a kind of deep freeze, too far from the sun to experience the warming that drives the geological activity seen on inner solar system bodies. They are, in a sense, fossils, remnants of the original disk of gas and dust from which everything in the solar system, including the Earth, was assembled. As the Voyager spacecraft moved outward through the 1980s and 1990s, the instruments aboard them continued to function, sending back measurements of the environment through which they were passing. The solar wind, the continuous stream of charged particles flowing outward from the sun, was still detectable, still pushing outward in all directions. The sun's magnetic field, carried along by the solar wind, was still present, still organizing the local environment in ways that the magnetometers could track. But both were growing weaker. The solar wind was thinning as it spread across an ever larger volume of space. The magnetic field was fading gradually into the background. The scientists monitoring both spacecraft understood that they were approaching something, even if the precise nature and location of that something was uncertain. Theoretical models had predicted that at some distance from the sun, the solar wind would encounter the interstellar medium, the diffuse gas and magnetic fields that fill the space between star systems, and that this encounter would produce a series of boundary regions. But no spacecraft had ever traveled far enough to reach those regions. The predictions were based on theory and indirect observation. What Voyager would actually find there was an open question. In the meantime, the spacecraft themselves were aging. Systems that were no longer needed had been shut down to conserve power. The cameras, which had served their purpose during the planetary encounters, were turned off. The radioisotope thermoelectric generators that powered each spacecraft were producing less electricity with each passing year, as the plutonium-238 fuel inside them slowly decayed. Engineers at the Jet Propulsion Laboratory managed this slow decline carefully, making decisions about which instruments to keep running and which to sacrifice, always with the goal of preserving the most scientifically valuable sensors for as long as possible. There was something quietly remarkable about this phase of the mission. Two spacecraft, built with 1970s technology, were operating in a region of space no instrument had ever sampled. The data they were returning had no precedent. Every reading was new information, adding detail to a picture of the outer solar system that had previously existed only in theoretical models. The scientists receiving that data knew that what Voyager was doing could not be repeated quickly. No other spacecraft was on its way to the outer solar system. The measurements being taken in those years were, for the foreseeable future, the only measurements that would ever be taken from that distance. The outer dark, as those years of quiet transit might be called, was not a dramatic phase of the mission. There were no planetary flybys, no close encounters with moons or ring systems, no images of alien landscapes. There was only the gradual accumulation of data points, the slow passage of distance, and the knowledge that somewhere ahead the boundary was waiting. Chapter 4. The Heliosphere. To understand what Voyager was approaching, it helps to understand what the Sun actually does to the space around it. The Sun is not a passive object sitting quietly at the center of the solar system. It is continuously active, continuously producing, continuously pushing outward in all directions. And the most significant thing it pushes outward is not light, but a stream of charged particles. The solar wind, as this stream is called, originates in the Sun's outer atmosphere, a region called the corona. The corona is extraordinarily hot, reaching temperatures of several million degrees, far hotter than the visible surface of the Sun below it. The reasons for this temperature difference are still not entirely resolved and remain an active area of research in solar physics. But the consequence is clear. At those temperatures, the particles in the corona have enough energy to escape the Sun's gravity entirely. They flow outward in all directions, a continuous current of electrons and protons moving at speeds typically between 300 and 800 kilometers per second. This solar wind does not simply blow outward and then stop at some arbitrary distance. It keeps going, filling an enormous volume of space with the Sun's material. As it travels, it carries with it the Sun's magnetic field, stretched and wound into a spiral shape by the Sun's rotation. This combination of solar wind plasma and embedded magnetic field creates a vast bubble of solar influence that surrounds the entire solar system. That bubble is called the heliosphere. The heliosphere is not a small structure. At its widest, it extends somewhere between 80 and 100 astronomical units from the Sun in the direction facing into the flow of the interstellar medium, and considerably further in the opposite direction, where the solar wind pushes out a long trailing structure sometimes compared to the tail of a comet. The exact shape and dimensions of the heliosphere have been subjects of ongoing research and revision, and Voyager's measurements have contributed significantly to refining those estimates. Inside the heliosphere, the environment is dominated by the Sun. The solar wind fills this space with a thin but measurable plasma. The Sun's magnetic field organizes the behavior of charged particles throughout the region. Cosmic rays, high-energy particles arriving from outside the solar system, are partially deflected and absorbed by the heliosphere, so that the interior of the bubble is somewhat shielded from the full intensity of interstellar radiation. This shielding effect is one of the heliosphere's most significant properties from the perspective of life on Earth. Without it, the level of cosmic ray radiation reaching the inner solar system would be considerably higher. The boundary of the heliosphere is not a sharp line. It is a transition zone, a region where the solar wind gradually gives way to the interstellar medium. But within that transition zone, physicists had predicted the existence of several distinct features, places where measurable changes in the environment would signal a shift from one regime to another. The outermost of these features, the Heliopause, was understood to be the true boundary, the place where the Sun's influence finally ends and interstellar space begins. But before reaching the Heliopause, a spacecraft traveling outward would first encounter something called the termination shock. The concept of a termination shock comes from fluid dynamics. When a supersonic flow encounters an obstacle or a region of higher pressure, it cannot simply slow down gradually. The transition is abrupt, forming a shock wave, a boundary across which the speed, density, temperature, and other properties of the flow change suddenly. The solar wind travels outward at supersonic speeds relative to the interstellar medium. When it finally encounters the pressure of that medium, it must slow down, and the slowing happens at a shock front. On the near side of the termination shock, the solar wind is fast, thin, and cool by plasma standards. On the far side, it is slower, denser, and hotter. Beyond the termination shock lies a region called the Heliosheath. This is the outer layer of the heliosphere, the zone between the termination shock and the heliopause. The Heliosheath is where the solar wind, having slowed at the shock, continues to move outward, but now in a more turbulent and compressed state. It is a transition region, neither fully solar nor fully interstellar, and it was almost entirely unknown before Voyager reached it. All of this had been predicted, modelled, and debated for decades before any spacecraft got close enough to test the predictions. The models agreed on the basic structure, but disagreed on the details, the distances involved, the thickness of the Heliosheath, the precise nature of the Heliopause. When Voyager 1 began approaching the Termination Shock in the early 2000s, it was carrying the only instruments that had ever been in a position to find out which predictions were right. Chapter 5: The Termination Shock. In the early 2000s, Voyager 1 was approaching a distance of roughly 80 astronomical units from the Sun. At that distance, the signals it sent back took more than 11 hours to reach Earth. The spacecraft was moving at about 17 kilometers per second relative to the Sun, which sounds fast, but translates to covering only about 3.5 astronomical units per year. At that pace, the outer boundaries of the solar system were still years away. The scientific team monitoring Voyager 1 knew that the termination shock was somewhere in the region ahead. The theoretical predictions placed it somewhere between 80 and 100 astronomical units, though the uncertainty in those estimates was considerable. The heliosphere is not a static structure. It breathes, in a sense, expanding and contracting in response to changes in solar activity. During periods of higher solar activity, when the Sun produces more energetic outflows, the solar wind pushes outward more forcefully, and the termination shock moves farther from the Sun. During quieter periods, it moves inward. This variability meant that pinpointing the shock's location in advance was genuinely difficult. The first indication that Voyager 1 was approaching the termination shock came from its cosmic ray detectors. Cosmic rays are high-energy particles, primarily protons, that originate outside the solar system and stream inward from all directions. The heliosphere partially shields the inner solar system from these particles, but near the termination shock, the shielding becomes less effective. As Voyager 1 moved outward, its cosmic ray detectors began registering an increase in the intensity of these particles, suggesting that the spacecraft was moving into a region of reduced shielding. At the same time, the instruments measuring the solar wind were detecting changes in its behavior. The wind was becoming more variable, more turbulent, showing signs of the kind of disturbance that would be expected as a supersonic flow approached its shock boundary. There were periods when the data suggested Voyager 1 might have already crossed the shock, followed by periods when the readings reversed, suggesting that the shock had moved outward past the spacecraft again. The heliosphere was indeed breathing, and the termination shock was moving back and forth across Voyager 1's position as solar activity fluctuated. This back and forth made it difficult to identify a single clean crossing event. But by late 2004, when Voyager 1 was at approximately 94 astronomical units from the Sun, the evidence had accumulated sufficiently for scientists to conclude that the spacecraft had crossed the termination shock. The solar wind speed had dropped sharply, consistent with the deceleration expected at a shock boundary. The magnetic field strength had increased. The temperature of the plasma had risen. These changes, taken together, matched the theoretical predictions for what a spacecraft would measure as it crossed from the supersonic solar wind into the slower, denser, hotter region beyond. Voyager 2 crossed the termination shock in August of 2007 at a distance of approximately 84 astronomical units. The fact that Voyager 2 crossed at a closer distance than Voyager 1 was itself informative. The two spacecraft were traveling in different directions. Voyager 1 heading northward out of the plane of the solar system, and Voyager 2 heading southward. The difference in crossing distances suggested that the heliosphere is not perfectly symmetrical, that the termination shock is closer to the Sun in the direction Voyager 2 was traveling than in the direction Voyager 1 had gone. This asymmetry was likely caused by the motion of the solar system through the interstellar medium, which compresses the heliosphere on the side facing into the flow and allows it to extend further on the trailing side. The Voyager 2 crossing was in some ways more informative than that of Voyager 1, because Voyager 2 was carrying a functioning plasma science instrument that Voyager 1's corresponding instrument had lost years earlier. This instrument could directly measure the properties of the solar wind plasma, providing detailed readings of how the wind speed, density, and temperature changed as the spacecraft crossed the shock. The data confirmed the basic picture that had been inferred from Voyager 1's indirect measurements, while adding quantitative detail that refined the theoretical models considerably. One finding from the termination shock crossings that surprised scientists was related to the behavior of energetic particles. The models had predicted that the termination shock would be an efficient accelerator of particles, boosting their energies as they bounce back and forth across the shock boundary. This process, called diffusive shock acceleration, is believed to be responsible for producing cosmic rays in various astrophysical settings. But the particle energies measured by Voyager at the termination shock were lower than expected. The shock was accelerating particles, but not as efficiently as the models had suggested. This discrepancy prompted a reassessment of the acceleration mechanisms at work and pointed toward a more complex picture of how the termination shock processes the particles that encounter it. What lay immediately beyond the termination shock was the Heliosheath, and it was into this unknown region that both Voyager spacecraft now moved, carrying their aging instruments into territory that no human-made object had ever sampled. Chapter 6. The Heliosheath. Beyond the termination shock, the solar wind does not disappear. It continues moving outward, but it has been fundamentally changed by its passage through the shock. It is slower now, compressed, and considerably hotter than it was before. It moves through the Heliosheath in a more turbulent and disordered way, no longer the relatively smooth supersonic flow it had been closer to the Sun. This is the environment that both Voyager spacecraft entered after their respective termination shock crossings, and it turned out to be stranger and more complex than the models had anticipated. The Heliosheath had been predicted to exist, but its internal structure was largely unknown before Voyager reached it. The theoretical models described it as a relatively uniform transition zone, a buffer between the ordered solar wind and the interstellar medium beyond. What Voyager found instead was a region of considerable variability, with large-scale structures, unexpected magnetic configurations, and particle populations that did not behave as cleanly as the models had suggested. One of the more surprising findings involved the magnetic field within the Heliosheath. Scientists had expected that the Sun's magnetic field, carried outward by the solar wind, would maintain a relatively organized structure even in this outer region. Instead, the magnetometer readings showed a field that was highly variable, with sectors of different polarity arranged in a complex pattern. The solar wind carries magnetic field lines rooted in the Sun, and as the Sun rotates, these field lines are wound into a spiral. In the inner heliosphere, this spiral structure is fairly well ordered, but in the Heliosheath, the compression and turbulence appeared to fold and bunch the field lines into irregular configurations that the models had not predicted. The behavior of energetic particles in the heliosheath was also more complex than expected. Both spacecraft measured populations of particles streaming inward from the direction of the heliopause, as well as particles moving outward from the termination shock. These competing flows created a complicated particle environment that was difficult to interpret cleanly. Some of the particle populations appeared to be cosmic rays leaking inward through the heliopause, while others seemed to be solar wind particles that had been accelerated and redirected by the magnetic structures within the Heliosheath. Voyager 1 spent approximately 8 years traversing the Heliosheath before reaching the Heliopause. During that time, it covered a distance of roughly 30 astronomical units, suggesting that the Heliosheath in the direction Voyager 1 was traveling was considerably thicker than many models had predicted. Voyager 2, traveling in a different direction, spent a similar number of years in the Heliosheath, crossing it at a slightly different thickness. The comparison between the two spacecraft's measurements provided the first opportunity to assess how the Heliosheath varies with direction, confirming that the heliosphere is indeed asymmetric in ways that reflect both the Sun's activity and its motion through the local interstellar medium. One particularly significant set of observations from the Heliosheath involved the detection of energetic neutral atoms. These are particles that originate as charged ions in the Heliosheath and the interstellar medium, but which exchange an electron with a neutral atom and become electrically neutral themselves. Because they carry no charge, they are not deflected by magnetic fields and can travel in straight lines across vast distances. By detecting these particles and measuring the directions from which they arrived, scientists were able to construct maps of the Heliosheath structure from instruments aboard spacecraft much closer to the Sun. The IBEX mission, launched in 2008, was specifically designed to make such measurements, and its findings were compared with Voyager's in situ data to build a more complete picture of the Heliosheath's properties. Among IBEX's most striking findings was the detection of a ribbon of enhanced energetic neutral atom emission, wrapping around the heliosphere in a broad arc. This ribbon did not correspond obviously to any feature predicted by the existing models, and its origin remained debated for years. Some researchers proposed that it was produced by the interaction between the heliosphere's magnetic field and the interstellar magnetic field at the heliopause, while others suggested it reflected the structure of the local interstellar medium in the vicinity of the solar system. The ribbon remains an active subject of research, one of several mysteries that Voyager's journey helped to reveal without fully resolving. As Voyager 1 continued outward through the Heliosheath in the years after 2004, the scientific team watched its instruments carefully for signs of the heliopause. The heliopause would be marked by a set of specific changes: a drop in the solar wind density to near zero, a sharp increase in cosmic ray intensity, and a change in the magnetic field direction reflecting the transition from the Sun's field to the interstellar field. These signatures would not all appear simultaneously, and distinguishing a genuine heliopause crossing from a temporary excursion caused by the heliosphere's breathing would require careful analysis of data from multiple instruments simultaneously. The team knew the crossing was coming. They did not know exactly when. And in the years approaching 2012, the readings from Voyager 1 began to change in ways that suggested the boundary was near. Chapter 7: Crossing the Heliopause. In the years leading up to 2012, the instruments aboard Voyager 1 were telling a story that the scientific team was reading carefully and sometimes debating intensely. The data was not straightforward. The Heliopause, the boundary between the Sun's domain and interstellar space, was not announcing itself with a single clean signal. It was revealing itself gradually, in the way that most things in nature reveal themselves, through an accumulation of small changes, each one individually ambiguous, but collectively pointing towards something significant. The first clear indication came from the cosmic ray detectors. Throughout Voyager 1's transit of the Heliosheath, these instruments had been measuring two distinct populations of high-energy particles. One population consisted of anomalous cosmic rays, particles that originate within the heliosphere itself, accelerated at the termination shock, and then trapped within the Heliosheath by the surrounding magnetic field. The other population consisted of galactic cosmic rays, true interstellar particles arriving from outside the solar system entirely. As Voyager 1 approached the Heliopause, the anomalous cosmic ray counts began to drop, while the galactic cosmic ray counts began to rise. This was exactly what the models predicted would happen near the boundary. In May of 2012, the anomalous cosmic ray intensity dropped sharply and dramatically. Within a matter of days, it fell to nearly zero. At the same time, the galactic cosmic ray intensity jumped by more than 9%. This was a striking change, and it sent a wave of excitement through the scientific team. It looked, in those first readings, as though Voyager 1 had crossed the Heliopause. But then something unexpected happened. The magnetic field direction did not change. The models had predicted that crossing the Heliopause would produce a clear shift in the magnetic field orientation, because the Sun's magnetic field and the interstellar magnetic field were expected to be aligned differently. Voyager 1's magnetometer showed no such shift. The field direction remained essentially the same on both sides of what the particle data suggested was a boundary. This was puzzling. Either the crossing had not actually happened, or the interstellar magnetic field near the Heliopause was aligned more closely with the Sun's field than the models had anticipated. Over the following months, the particle data continued to show the sharp drop in anomalous cosmic rays and elevated galactic cosmic ray levels that had appeared in May. There were brief, partial recoveries, suggesting that the Heliosphere was still breathing and that Voyager 1 was near the boundary rather than definitively beyond it. Then, in late August of 2012, the plasma wave instrument aboard Voyager 1 detected oscillations in the local plasma that allowed scientists to measure the density of the material surrounding the spacecraft. The density was approximately 40 times higher than it had been in the Heliosheath. This was consistent with the known density of the local interstellar medium and inconsistent with any known region within the heliosphere. This plasma density measurement, combined with the cosmic ray data, provided the basis for the announcement made in September of 2013, when NASA confirmed that Voyager 1 had entered interstellar space. The crossing was dated to around August 25, 2012, when the particle populations had shifted most decisively. At that moment, Voyager 1 was approximately 121 astronomical units from the Sun. The signal confirming the crossing had taken more than 16 hours to travel from the spacecraft to the receivers on Earth. The absence of a magnetic field direction change remained a subject of discussion and research after the announcement. Some scientists proposed that the interstellar magnetic field in the immediate vicinity of the Heliopause had been draped and realigned by its long interaction with the heliosphere, so that it happened to be oriented similarly to the Sun's field in that region. Others suggested that the models of the interstellar magnetic field needed revision. The debate contributed to a broader reassessment of the Heliopause's structure and the nature of its interaction with the interstellar medium. Voyager 2's Heliopause crossing came in November of 2018 at a distance of approximately 119 astronomical units from the Sun. This crossing was in some ways cleaner and more informative than Voyager 1's, partly because Voyager 2 still had its functioning plasma science instrument, which could directly measure the properties of the plasma on both sides of the boundary. The data from Voyager 2 confirmed the sharp transition from heliospheric to interstellar plasma, and showed that the heliopause in the direction Voyager 2 was traveling was relatively thin. The transition happened over a distance of less than 1 astronomical unit, a remarkably abrupt change given the vast scales involved. One of the more surprising findings from Voyager 2's crossing was a thin layer of hot plasma just inside the heliopause. This layer had not been predicted by the models, and its origin was not immediately clear. One interpretation was that it represented solar wind plasma that had been heated and compressed as it approached the heliopause, creating a boundary layer of unusually energetic material just before the transition to interstellar space. Another interpretation involved the mixing of heliospheric and interstellar material at the boundary, a process that the models had not captured in sufficient detail. This hot layer became one of several new features that the Voyager crossings added to the scientific picture of the heliosphere's outer edge. Both crossings taken together provided something that no single spacecraft could have delivered: a comparison between two different points on the heliopause, separated in direction and measured years apart. The similarities between the two crossings confirmed the broad theoretical framework that had been built up over decades of modelling. The differences pointed toward the ways in which the heliosphere is more complex, more variable, and more asymmetric than the simplest models had assumed. Both kinds of information, the confirmations and the surprises, were exactly what a mission of this kind is designed to produce. Chapter 8. What the data revealed. The crossing of the heliopause was not the end of Voyager's scientific contribution. It was, in many ways, the beginning of a new phase. Both spacecraft were now operating in interstellar space, sampling an environment that had never been directly measured before. The data they were returning was not just confirming or refining existing models. It was providing the first ground truth measurements of the local interstellar medium, the actual material that fills the space between our solar system and the nearest stars. The local interstellar medium is not empty. It is a diffuse mixture of gas, dust, magnetic fields, and energetic particles. Most of the gas is hydrogen, with helium making up the majority of the remainder. The density is extraordinarily low by everyday standards, roughly 1 atom per cubic centimeter on average, compared to the approximately 10 billion atoms per cubic centimeter in the air we breathe. But across the vast distances of interstellar space, even this thin material accumulates into something measurable and significant. Before Voyager, measurements of the local interstellar medium had been made remotely, using instruments on spacecraft and telescopes that could detect radiation and particles arriving from interstellar space. These remote measurements provided useful information, but they were indirect. They told scientists something about the average properties of the interstellar medium over large volumes of space, without being able to resolve local variations or provide the kind of detailed point-by-point sampling that in situ measurements make possible. Voyager's instruments, operating directly within the interstellar medium, provided something qualitatively different. The plasma wave instrument, which had played a key role in confirming both heliopause crossings, continue to operate in interstellar space and continue to provide valuable data. By detecting oscillations in the plasma triggered by energetic events on the Sun, the instrument allowed scientists to measure the density of the interstellar plasma at Voyager's location at different times. These measurements showed that the density of the interstellar medium varies, even over relatively small regions. The local interstellar medium is not uniform. It has structure with denser and less dense regions, and the solar system is moving through this structured environment continuously. The magnetic field measurements in interstellar space provided another set of surprises. The strength and direction of the interstellar magnetic field near the Heliopause had implications for models of how the heliosphere is shaped and oriented. The field measured by Voyager 1 in interstellar space was stronger than many pre-crossing models had predicted, and its direction, while broadly consistent with estimates derived from remote observations, differed in detail from some of the most widely used models. These discrepancies prompted revisions to the models and raised questions about the large-scale structure of the magnetic field in the solar neighborhood. The cosmic ray environment in interstellar space was also informative. Inside the heliosphere, the solar wind and magnetic field partially shield the inner regions from galactic cosmic rays, so that the intensity of these particles increases with distance from the Sun. Once Voyager 1 crossed the Heliopause, the cosmic ray intensity rose to a level that remained essentially constant, no longer increasing with distance. This plateau was significant. It suggested that the cosmic ray intensity measured by Voyager 1 in interstellar space was representative of the local interstellar cosmic ray background, the baseline level of high-energy particle radiation that exists throughout this region of the galaxy, unmodified by the Sun's influence. This cosmic ray background has implications that extend beyond the immediate vicinity of the solar system. Cosmic rays are known to play a role in the chemistry of interstellar gas clouds, ionizing molecules and driving chemical reactions that would not otherwise occur. They also interact with the magnetic fields threading through the galaxy, and their distribution and intensity provide information about the history of energetic events, supernovae for instance, that have occurred in the galactic neighborhood over millions of years. Voyager's direct measurement of the local cosmic ray background gives scientists a precise reference point for understanding these broader processes. The energetic particle data from interstellar space also revealed something about the structure of the heliopause itself. Even after both spacecraft had crossed into interstellar space, their instruments continued to detect occasional bursts of particles that appeared to originate from within the heliosphere, leaking outward through the boundary. These leakage events provided information about how permeable the heliopause is to different types of particles, and how the boundary mediates the exchange of material between the heliosphere and the interstellar medium. The heliopause, it became clear, is not a perfectly sealed boundary. It is more like a semi-permeable membrane, allowing some particle populations to pass through while deflecting others. One of the more philosophically striking aspects of the data returned from interstellar space was what it said about the Sun's place in its galactic environment. The local interstellar medium through which Voyager is now traveling is part of a larger structure called the local bubble, a region of hot, low-density plasma, roughly 1,000 light-years across, believed to have been excavated by a series of supernova explosions over the past few tens of millions of years. The solar system entered this bubble somewhere between 5 and 10 million years ago, and has been moving through it since. The properties of the interstellar medium that Voyager is sampling, its density, temperature, magnetic field strength, and cosmic ray content are all characteristic of this local bubble environment. The data also raised questions that will take years or decades to fully answer. The structure of the interstellar magnetic field, the variability of the interstellar plasma density, the detailed mechanisms by which the heliopause mediates particle exchange. All of these are subjects of ongoing research, with Voyager's measurements providing the primary observational constraints. In this sense, the mission's scientific contribution is still unfolding, still accumulating, still generating new questions, even as it answers old ones. Chapter 9. Interstellar Space. The word interstellar carries a weight that is difficult to fully absorb. It means between the stars. It describes the vast regions of space that separate one stellar system from another. Regions so large that even light, traveling at nearly 300,000 kilometers per second, takes years to cross them. When Voyager 1 entered interstellar space in 2012, it did not arrive somewhere new in the way that a ship arrives at a port. It crossed a threshold into an environment that is defined primarily by the absence of the sun's direct influence and by the presence of something older and more diffuse, the background material of the galaxy itself. The nearest star to our solar system is Proxima Centauri, a small red dwarf located approximately 4.24 light-years away. At Voyager 1's current speed of roughly 17 kilometers per second, it would take approximately 73,000 years to travel that distance if it were headed in that direction. It is not. Voyager 1 is moving toward the constellation Ophiuchus, and the nearest star in roughly that direction is considerably further away. In any meaningful human sense, Voyager will never reach another star. It will drift through interstellar space indefinitely, long after its instruments have fallen silent, and long after the civilization that built it has changed beyond recognition. This context is important for understanding what interstellar space actually is in practical terms. It is not a destination. It is a medium, a thin, cold, magnetized plasma threaded with cosmic rays and dust, extending in all directions for light years between the islands of warmth and light that stars represent. The solar system is one of those islands. The space Voyager now occupies is the ocean between islands, and it is almost incomprehensibly vast. The interstellar medium in the vicinity of the solar system has a temperature that might seem paradoxical. Despite being far from any star, the local interstellar medium is actually quite hot by the standards of interstellar gas, somewhere in the range of 6,000 to 10,000 degrees Kelvin. This temperature does not mean the material is warm in any everyday sense, because the density is so low that the total energy content per unit volume is negligible. Temperature in a plasma describes the average kinetic energy of individual particles, not the thermal energy available to heat an object placed within it. A spacecraft moving through this hot but thin plasma does not experience warmth. It experiences cold, because the dominant energy exchange is through radiation, and the spacecraft radiates heat into a surrounding environment that is, from a radiation perspective, essentially at absolute zero. The magnetic field threading through the local interstellar medium is another defining feature of this environment. Magnetic fields in space are not produced by magnets in the conventional sense. They are maintained by the motion of charged particles, the plasma itself, and they are ancient, having been generated and amplified over billions of years of galactic history. The field measured by Voyager in the interstellar medium, near the Heliopause, has a strength of roughly 5 to 6 microgauss, which is extraordinarily weak by everyday standards, but sufficient to influence the behavior of charged particles over large distances. This field plays a role in shaping the heliosphere from the outside, pressing against it and orienting it in ways that are still being worked out from Voyager's data. The dust component of the interstellar medium, while not directly measurable by Voyager's instruments, is worth noting because of what it represents. Interstellar dust grains are tiny solid particles, typically a fraction of a micrometer in size, composed of silicates, carbonaceous material, and various ices. They form in the atmospheres of dying stars and are expelled into interstellar space when those stars shed their outer layers or explode. Over billions of years, this dust has been processed, destroyed, and reformed through cycles of stellar birth and death. The atoms in these dust grains, and in the gas of the interstellar medium, are the raw material from which future stars and planetary systems will eventually form. In a very real sense, the interstellar medium that Voyager is now moving through is both the remnant of past stellar generations and the reservoir from which future ones will emerge. The silence of interstellar space is perhaps its most defining characteristic, though silence is a human concept that requires some translation to apply here. There are no sound waves in interstellar space, because the density of the medium is far too low to support them. There is electromagnetic radiation of various kinds, including radio waves, microwaves, and high-energy cosmic ray particles. There are the slow oscillations of the plasma that Voyager's instruments can detect. But compared to the inner solar system, where the solar wind creates a continuous dynamic environment of waves and fluctuations, the interstellar medium near the Heliopause is relatively quiet. The fluctuations are smaller, the changes slower, the environment more stable. This relative stability is one of the things that makes the interstellar medium scientifically interesting as a long-term sampling environment. Voyager's instruments, to the extent that they continue to function, are building up a record of conditions at a single point in interstellar space over a span of years. This kind of time series data is valuable because it can reveal how the local interstellar medium changes over time. Whether those changes reflect variations in the interstellar medium itself, or variations in the heliosphere that propagate outward and affect the boundary region, or both. No remote observation could provide this kind of continuous local record. What Voyager is traversing right now, in the years since its Heliopause crossings, is a region of interstellar space that is geologically and astronomically close to the solar system. Close, that is, on galactic scales, which means within a few light years. This region is part of the local interstellar cloud, a slightly denser and cooler pocket of gas within the broader local bubble. The solar system has been moving through this cloud for roughly 60,000 to 100,000 years, and will exit it within the next few thousand years, entering a different region of the local bubble with slightly different properties. Voyager's measurements of this cloud, taken from within it rather than from outside, are among the most direct observations of the cloud's properties that have ever been made. There is something quietly extraordinary about the fact that the data Voyager returns each day represents a measurement of a place and an environment that no human will ever visit, that no other instrument is currently sampling, and that will not be sampled again by any planned mission for the foreseeable future. Each reading is unique. Each data point adds something that did not exist in the scientific record before, and all of it is being gathered by instruments designed and built more than 4 decades ago, traveling on a trajectory that was calculated before personal computers existed, still doing their work in the cold and the dark between the stars. Chapter 10. Voyager 2 follows. While much of the public attention surrounding the Voyager program focused on Voyager 1, Its twin had been conducting its own remarkable journey through the outer solar system and beyond. Voyager 2 followed a different path, one that took it past all 4 outer planets before sending it on a southward trajectory out of the plane of the solar system. By the time Voyager 1 was making headlines with its Heliopause crossing in 2012, Voyager 2 was still traversing the Heliosheath, its instruments quietly gathering data from a direction that no spacecraft had ever sampled before. The 6-year gap between the 2 Heliopause crossings was not simply a consequence of Voyager 2 traveling more slowly. It reflected the asymmetry of the heliosphere itself. Voyager 1 was traveling northward and slightly in the direction that the solar system is moving through the interstellar medium. Voyager 2 was traveling southward and in a different azimuthal direction. The heliosphere, as Voyager's data had already suggested, is not a perfect sphere. Its shape is influenced by the pressure of the interstellar medium flowing past it, by the structure of the interstellar magnetic field, and by variations in the solar wind output in different directions. The result is an asymmetric structure whose boundaries are closer to the Sun in some directions than in others. Voyager 2's crossing of the Heliopause in November of 2018 was anticipated with considerable scientific excitement, precisely because it offered a second sampling point on the Heliopause at a different location and a different time. The scientific value of having 2 spacecraft make this crossing cannot be overstated. A single measurement always carries the ambiguity of not knowing whether what was measured is representative or anomalous. 2 measurements made in different directions allow that ambiguity to be partially resolved. Where the 2 crossings agreed, the agreement provided confidence that the measurements reflected real properties of the Heliopause rather than local anomalies. Where they differed, the differences pointed toward genuine variations in the heliosphere's structure. The crossings agreed on several fundamental points. Both showed a sharp transition from heliospheric to interstellar plasma, with the solar wind density dropping to near zero and the interstellar plasma density rising to levels consistent with remote observations. Both showed a significant jump in galactic cosmic ray intensity at the boundary. Both showed that the Heliopause, despite being the product of the continuous interaction between 2 large-scale plasma environments over billions of years, is a surprisingly thin and well-defined boundary rather than a broad and gradual transition zone. The differences were equally informative. Voyager 2's crossing occurred at a distance of approximately 119 astronomical units, slightly closer to the Sun than Voyager 1's crossing at 121 astronomical units. Given that the 2 spacecraft were traveling in different directions, this small difference in crossing distance added a data point to the ongoing effort to map the shape of the heliosphere. The Heliosheath that Voyager 2 traversed appeared to be somewhat thinner in its direction of travel than the Heliosheath Voyager 1 had crossed, though the comparison is complicated by the fact that the crossings occurred at different phases of the solar activity cycle. The most significant advantage Voyager 2 brought to its Heliopause crossing was its functioning plasma science instrument. This instrument had been measuring the properties of the solar wind plasma continuously throughout Voyager 2's journey, and it continued to function as the spacecraft approached and crossed the Heliopause. The direct plasma measurements it provided allowed scientists to track the changes in the solar wind speed, density, and temperature as the spacecraft moved through the Heliosheath and crossed into interstellar space. These measurements confirmed and quantified what Voyager 1's indirect observations had suggested, and they provided a level of detail about the plasma environment at the Heliopause that had not been available from Voyager 1's crossing. Among the most notable findings from Voyager 2's plasma data was the measurement of a thin layer of unusually hot plasma just inside the heliopause. This layer, with temperatures significantly higher than the surrounding Heliosheath plasma, appeared to represent a zone where solar wind material was being heated and compressed as it approached the boundary. The existence of this hot layer had not been clearly predicted by the models, and its detection prompted a reassessment of the processes occurring at the heliopause. One interpretation was that the layer was produced by the reconnection of magnetic field lines at the boundary, a process in which oppositely directed field lines break and reconnect, releasing energy into the surrounding plasma. Another interpretation involved the thermalization of energetic particles that had been accelerated at the termination shock and were now losing energy as they approached the heliopause. Distinguishing between these possibilities required careful modeling, and the debate continued for several years after the crossing. Voyager 2's data also provided new information about the interstellar magnetic field immediately outside the heliopause. While the field direction was broadly consistent with what Voyager 1 had measured in a different part of the sky, the field strength showed some differences, suggesting that the interstellar magnetic field has a degree of spatial variation in the immediate vicinity of the heliopause. This variation could reflect the draping of interstellar field lines around the heliosphere, a process analogous to the way a river's current wraps around a large obstacle, or it could reflect genuine spatial variation in the local interstellar medium. Separating these effects required modeling that incorporated both spacecraft's measurements simultaneously. The two Voyager spacecraft are now both operating in interstellar space, traveling in different directions and separated by a distance that grows larger every year. They represent two sampling points in an environment that is otherwise unmeasured by any in situ instrument. The data they return, though limited by their aging power systems and the gradual shutdown of instruments over time, remains irreplaceable. No other spacecraft is currently traveling toward the heliopause. No other mission is planned that would place instruments in the local interstellar medium within the next several decades. What Voyager provides, it provides uniquely, and the scientific community receives each new transmission with the awareness that these signals are coming from a place that nothing else we have built has ever reached. Chapter 11. The Pale Blue Dot. On February 14, 1990, Voyager 1 turned its camera backward toward the inner solar system and took a series of photographs. This was not a routine scientific observation. The cameras had been essentially retired after the Saturn encounter nearly a decade earlier, their primary mission complete. Turning them on again required a deliberate decision, one that had been advocated for years by the astronomer Carl Sagan, who understood that the opportunity to photograph the solar system from such an extreme distance would not come again. The resulting images showed the planets as faint points of light against the darkness of space. Earth appeared as a tiny, pale blue dot, less than a pixel across in the original image, suspended in a beam of scattered sunlight. The image was taken from a distance of approximately 6 billion kilometers, or about 40 astronomical units. It was the most distant photograph of Earth ever taken at that time, and it remains among the most distant ever taken. Sagan wrote about that image in terms that have stayed with many people who encountered them. He described the Earth as a mote of dust suspended in a sunbeam, and reflected on what the image reveals about the place of humanity in the cosmos. Every person who has ever lived, every king and peasant, every act of courage and cruelty, every invention and discovery, every civilization that has risen and fallen, All of it occurred on that pale blue dot. The image does not argue for any particular philosophical or political conclusion. It simply shows, with quiet clarity, the scale of the universe relative to the world we inhabit. The pale blue dot photograph has become one of the most reproduced and referenced images in the history of space exploration. But its significance is not primarily aesthetic or emotional, though it is both of those things. Its significance is also scientific, in the sense that it demonstrates what it means to observe a planet from interstellar distances. The Earth, with all its complexity, its oceans and continents, its atmosphere and life, is reduced at that distance to a point of light indistinguishable in scale from any other point of light in the field of view. This is the reality that astronomers confront when they study exoplanets, worlds orbiting other stars that appear, even through the most powerful telescopes, as nothing more than a faint signal in a sea of stellar light. The perspective offered by the pale blue dot image is also a perspective on distance itself. 6 billion kilometers is a large number, but it is a small fraction of the distance to even the nearest star. Proxima Centauri is roughly 40 trillion kilometers away. At the distance from which the pale blue dot was photographed, a spacecraft has barely left the neighborhood of the Sun. The true scale of interstellar space, the emptiness between stellar systems, is something that human intuition is not well equipped to grasp. The image, paradoxically, makes that scale more rather than less difficult to absorb, because it shows how vast even the inner solar system appears from a distance that is itself negligible on interstellar scales. In the years since 1990, Voyager 1 has continued moving outward, and the distance between it and Earth has continued to grow. By the early 2020s, it was more than 23 billion kilometers away. The sunlight reaching it at that distance is thousands of times fainter than what we receive on Earth. The Sun itself, seen from Voyager's current position, would appear as an exceptionally bright star, far outshining everything else in the sky, but still a point of light rather than a disk. The solar system, seen from that vantage point, would be invisible. The planets would be lost in the glare of the Sun, too faint and too close to it in angular terms to be resolved by any instrument Voyager carries. This invisibility of the planets from Voyager's current distance is a useful reminder of how the solar system appears from the perspective of the interstellar medium through which Voyager is traveling. To an observer in interstellar space, the solar system is not a sprawling collection of worlds and moons and rings and belts. It is a point source of light, a single star surrounded by an invisible heliosphere, embedded in the thin plasma of the local interstellar cloud. The richness and complexity of everything within the heliosphere is completely hidden from any external vantage point, just as the richness of any other stellar system is hidden from us. There is a kind of humility built into this perspective, and it is one that the Voyager mission has made concrete in a way that purely theoretical arguments cannot quite achieve. The image of the pale blue dot is not just a photograph. It is a demonstration of scale, a calibration of perspective, a reminder that the world we experience as vast and complex is, from a sufficient distance, indistinguishable from nothing at all. And the spacecraft that took that photograph has since traveled 3 times further from the Sun than it was when the shutter closed, and it is still, by cosmic standards, barely gone. Chapter 12. Still transmitting. One of the most quietly remarkable aspects of the Voyager mission is the fact that both spacecraft are still functioning. Not fully. Systems have been shut down, instruments have been lost, and the available power continues to decline with each passing year. but both spacecraft are still receiving commands from Earth, still gathering data from their remaining instruments, and still sending that data home across distances that continue to grow. For machines built in the early 1970s and launched nearly 5 decades ago, this represents an engineering achievement that was not guaranteed and is not taken for granted by the people who work with them. The power source for both Voyager spacecraft is a set of radioisotope thermoelectric generators, commonly referred to as RTGs. These devices produce electricity through a process called thermoelectric conversion, exploiting the temperature difference between a core of radioactive plutonium, 238, and the cold environment of space. As the plutonium decays, it produces heat, and that heat is converted directly into electricity by thermoelectric couples, solid-state devices with no moving parts, which is one of the reasons they have proven so durable. When the Voyager spacecraft launched in 1977, each RTG system was producing roughly 470 watts of electricity. By the mid-2020s, that figure had dropped to somewhere around 200 watts for each spacecraft, a decline of more than half over the course of the mission. This declining power budget has required a continuous process of difficult decisions. As the available electricity has decreased, instruments and systems that draw power have had to be turned off one by one to ensure that the most scientifically valuable instruments remain operational. The cameras were among the first major systems to be shut down after the planetary encounters were complete. Heater systems that kept instruments within their operating temperature ranges have been switched off for some subsystems, requiring engineers to assess whether those instruments could survive the cold of deep space without active heating. In several cases, instruments have survived temperatures far below their original design specifications, a testament to the robustness of the hardware. The communication system is among the most critical remaining functions. Both spacecraft transmit data using their large dish antennas, directed with considerable precision toward Earth. The signals they send are extraordinarily faint by the time they arrive, a fraction of a billionth of a watt, requiring the large dish antennas of NASA's Deep Space Network to detect them. The Deep Space Network operates receiving stations at 3 locations around the world in California, Spain, and Australia, positioned so that at least one station can maintain contact with any spacecraft at any time as the Earth rotates. Receiving Voyager's signals requires the network's largest antennas, some of them 70 meters across, pointed precisely at the spacecraft's location for hours at a time. The time delay in communications grows longer as the spacecraft travel further from Earth. In the mid-2020s, a signal sent to Voyager, one takes more than 22 hours to arrive, and another 22 hours pass before a response can return. Any command sent to the spacecraft must therefore be carefully considered in advance, because the round-trip communication time means that problems cannot be solved in real time. Engineers must anticipate issues, send instructions that account for multiple possible outcomes, and then wait nearly 2 days to learn whether their commands were received and executed as intended. This constraint shapes every aspect of how the spacecraft are operated in their current phase of the mission. In 2023, a significant problem emerged with Voyager 1 when the spacecraft began returning garbled data that was unreadable by the team on Earth. The issue was traced to a single chip in the flight data system, one of the computers aboard the spacecraft that packages scientific and engineering data for transmission. A portion of the chip's memory had become corrupted, likely due to decades of exposure to cosmic ray radiation in the harsh environment of interstellar space. The engineering team, working with documentation that was decades old and with software tools that bore little resemblance to modern computing environments, developed a solution that involved relocating the affected code to different parts of the computer's memory. The fix was implemented over a period of months, with each command taking more than 22 hours to arrive at the spacecraft. By the middle of 2024, Voyager 1 had returned to full operation, once again transmitting readable data from interstellar space. This episode illustrated both the fragility and the resilience of the mission. The spacecraft are old, and the environment they operate in is hostile to electronics in ways that accumulate over time. But the team supporting them has proven remarkably capable of solving problems remotely, across distances that dwarf anything previously attempted in the history of spacecraft operations. The fact that the team can even attempt such repairs depends on the survival of documentation, expertise, and institutional knowledge spanning nearly 5 decades. Itself a kind of organizational achievement that mirrors the technical one. The projected end of the Voyager mission is not a single event, but a gradual fading. As the RTG power output continues to decline, instruments will be shut down one by one over the coming years. The last scientific instrument is expected to fall silent sometime around 2025 to 2030, though the exact timing will depend on how carefully power is managed and which instruments prove most resilient to the cold. After that, the spacecraft will continue transmitting engineering data for some additional period, reporting on their own health and position until the power drops below the level needed to operate the transmitter. At that point, the signal will simply stop. There will be no dramatic final message, no planned shutdown command. The transmitter will fall silent, and 2 small machines will continue their journey through interstellar space in complete silence, carrying their golden records into a future that neither they nor we can see. Chapter 13. What Voyager changed. It is difficult to measure the full impact of a scientific mission while that mission is still ongoing. The Voyager program is now nearly 5 decades old, and its influence on planetary science, heliospheric physics, and the broader culture of space exploration has been so extensive and so deeply woven into subsequent work that separating it out cleanly is not entirely possible. But some of the ways in which Voyager changed things are clear enough to describe with confidence. The most immediate and concrete changes were to planetary science. Before Voyager, the outer solar system was known primarily through Earth-based telescopic observations, which could reveal the gross properties of the giant planets and their larger moons, but could not resolve surface features, detect geological activity, or measure atmospheric composition and structure in detail. Voyager transformed this picture entirely. The discoveries made during the planetary encounters of the late 1970s and 1980s, the volcanism of Io, the subsurface ocean of Europa, the complexity of Saturn's rings, the atmospheric chemistry of Titan, the geological diversity of Uranus's and Neptune's moon systems, redrew the map of the outer solar system and established research programs that continue to this day. The discovery of active volcanism on Io was perhaps the single most dramatic finding of the planetary phase. It demonstrated conclusively that geological activity is not limited to the inner solar system, and that tidal heating from gravitational interactions can sustain geological processes on bodies far from the Sun. This finding had implications that extended well beyond Io itself, suggesting that similar processes might be at work on icy moons throughout the outer solar system and, by extension, on moons orbiting planets in other stellar systems. The concept of a habitable zone which had previously been defined primarily in terms of distance from the host star and the availability of liquid water at the surface, was complicated and enriched by the recognition that tidal heating can maintain liquid water in subsurface environments at distances far beyond the traditional habitable zone boundaries. Europa's implied subsurface ocean, inferred from Voyager's images and subsequently confirmed and characterized by the Galileo mission in the 1990s and 2000s, became one of the most compelling targets in the search for life beyond Earth. The combination of liquid water, chemical energy sources, and the basic elements needed for organic chemistry makes Europa a plausible location for microbial life, and this possibility has driven the planning and funding of subsequent missions, including the Europa Clipper, launched in 2024, which is designed to characterize Europa's ocean and assess its habitability in detail. Beyond planetary science, Voyager changed the way scientists think about the heliosphere and the Sun's relationship to its galactic environment. Before Voyager, the heliosphere was a theoretical construct, predicted by models but unmeasured in its outer regions. The Termination Shock, the Heliosheath, and the Heliopause were features of those models, but their actual properties, their locations, their thicknesses, their internal structures, were uncertain. Voyager's traversal of all three boundary regions replaced theoretical uncertainty with observational data, providing the first direct measurements of the Sun's outer domain and its interface with interstellar space. These measurements changed the models in important ways. The Heliosheath proved to be thicker than many predictions had suggested. The Heliopause proved to be thinner and more abrupt. The magnetic field behavior at the boundary was more complex than anticipated. The cosmic ray environment in interstellar space was different in detail from what the models had predicted. Each of these discrepancies drove a cycle of model revision and refinement that has continued ever since, producing a progressively more accurate and nuanced understanding of how the Sun interacts with the broader galactic environment. Voyager also changed the practical and cultural understanding of what a space mission can be. When the Voyager spacecraft were designed, the concept of an interstellar mission was not part of the original scientific objectives. The primary mission was the planetary grand tour, and the possibility that the spacecraft might eventually reach interstellar space was understood but not central to the planning. The fact that both spacecraft have now done exactly that, have crossed the Heliopause and entered interstellar space, represents a kind of unplanned bonus, an extension of the mission far beyond its original scope, made possible by the durability of the hardware and the ingenuity of the team supporting it. This extension has demonstrated something important about the value of long-lived space missions. Scientific priorities change over time, and instruments that were designed to address one set of questions sometimes find themselves in a position to address entirely different questions that were not anticipated when they were built. The plasma wave instrument aboard Voyager 1, for example, was designed primarily for use during the planetary encounters. Its application to measuring plasma density in interstellar space decades later was an improvisation made possible by the instrument's survival and the team's creative thinking about how to use it in a new environment. This kind of adaptive reuse of scientific hardware requires institutional continuity, long-term funding commitments, and a willingness to keep supporting missions that have already accomplished their primary objectives. The cultural impact of Voyager is harder to quantify, but no less real. The golden records attached to both spacecraft have become one of the most widely recognized symbols of human outreach beyond the Earth, representing an aspiration toward contact and communication that transcends the purely scientific goals of the mission. The pale blue dot image has shaped how many people think about Earth's place in the cosmos. The names Voyager 1 and Voyager 2 are recognized by people who could not name any other spacecraft, and the idea that something built by human hands is now drifting through interstellar space carries an emotional resonance that extends well beyond the scientific community. What Voyager changed, in the end, is both specific and general. It changed specific scientific models and opened specific new areas of research. And it changed, more broadly, the sense of what is possible, what human ingenuity and patience and curiosity can accomplish when given sufficient time and sufficient commitment to see a journey through to wherever it leads. Chapter 14. The Oort Cloud and Beyond. Voyager 1 is in interstellar space, but it hasn't left the solar system, at least not in every sense of that phrase. The question of where the solar system ends depends on how you define it, and different definitions give very different answers. If the solar system is defined by the reach of the solar wind, then Voyager 1 crossed its boundary in 2012 when it passed through the Heliopause. But if the solar system is defined by the reach of the sun's gravity, then both Voyager spacecraft have a very long way to go before they can be said to have truly departed. The sun's gravitational influence extends far beyond the Heliopause. Gravity does not have a sharp boundary the way the solar wind does. It diminishes with distance according to an inverse square relationship, growing weaker but never reaching zero. At the distance Voyager 1 has currently reached, the sun's gravity is extraordinarily weak, but it is still the dominant gravitational influence in the local environment. There are no nearby stars whose gravity competes meaningfully with the sun's at that distance. Voyager is still, in the gravitational sense, a member of the solar system. The outer boundary of the sun's gravitational domain is thought to be marked by a vast and distant structure called the Oort cloud. This is a spherical shell of icy bodies believed to surround the solar system at distances ranging from roughly 2,000 to 100,000 astronomical units from the sun. To put that in perspective, the heliopause that Voyager 1 crossed lies at approximately 121 astronomical units. The inner edge of the Oort cloud is roughly 16 times further away than that. The outer edge is nearly 1,000 times further away than the heliopause. The Oort cloud has never been directly observed. No telescope has resolved individual Oort cloud objects in their distant orbits, and no spacecraft has traveled anywhere near it. Its existence is inferred primarily from the behavior of long-period comets. Comets, with orbital periods of hundreds or thousands of years that arrive in the inner solar system from random directions rather than from the flattened disk of the ecliptic plane. The random directions from which these comets arrive suggest that their source is a roughly spherical distribution of objects surrounding the solar system, rather than a flattened disk like the Kuiper belt. Occasional gravitational perturbations caused by passing stars or the tidal influence of the galactic disk dislodge objects from the Oort cloud and send them on long falling trajectories toward the inner solar system, where they become the long-period comets we observe. The objects in the Oort cloud are believed to have originated in the inner solar system, in the region where the giant planets were forming some 4.5 billion years ago. During that early period, gravitational interactions with the giant planets, particularly Jupiter and Saturn, flung enormous numbers of small icy bodies outward on highly elliptical orbits. Over time, the gravitational influence of the galactic environment rounded out the most elongated of these orbits, producing the roughly spherical distribution that characterizes the Oort cloud today. The objects themselves are pristine remnants of the early solar system, preserved in the deep cold at distances so great that the sun's warmth never reaches them in any meaningful way. Voyager 1 will reach the inner edge of the Oort cloud in roughly 300 years, assuming current estimates of the cloud's inner boundary are correct. It will take approximately 30,000 years to pass through the Oort cloud entirely and emerge on the other side. During that entire transit, the spacecraft will almost certainly be silent, its power long exhausted, its instruments dark. The golden record it carries will continue outward regardless, a physical artifact drifting through one of the most remote regions of the solar system's extended domain. The transit of the Oort cloud, when it eventually occurs, will represent the crossing of a threshold that is in some ways more philosophically significant than the Heliopause crossing. The Heliopause marks the end of the sun's direct physical influence through the solar wind. The outer edge of the Oort cloud marks the end of the sun's gravitational community, the point beyond which the objects one encounters are no longer bound to the sun and no longer part of the solar system in any meaningful sense. Beyond that boundary lies the true interstellar medium, the space between stellar systems, where no object owes its trajectory primarily to the sun's gravity. Between the solar system and the nearest stars, this true interstellar space is not entirely empty. The local bubble through which the solar system is moving contains diffuse gas and dust, cosmic rays, and a weak magnetic field. There are no known objects of significant size in the space between the solar system and Proxima Centauri, though the detection of such objects would be extraordinarily difficult given their expected faintness and the distances involved. The concept of interstellar objects passing through the solar system gained observational support in 2017 with the detection of 1I/Oumuamua, an object with a trajectory that was clearly hyperbolic. It was not bound to the sun and had arrived from interstellar space. A second interstellar visitor, 2I/Borisov, was detected in 2019. These detections confirmed that material does travel between stellar systems, carried on trajectories shaped by the gravitational dynamics of the galaxy over long timescales. Voyager will eventually join that population of interstellar travelers, though on a timescale that is difficult to hold in mind. In roughly 40,000 years, Voyager 1 will pass within approximately 1.6 light-years of the star Gliese 445, a red dwarf in the constellation Camelopardalis. This will be the closest approach to any star that either Voyager spacecraft will make for tens of thousands of years. It is not a close approach in any practical sense. 1.6 light-years is still a vast distance, but it is the nearest thing to a stellar encounter that Voyager's calculated trajectory produces within a foreseeable timeframe. After that encounter, Voyager will continue outward, its trajectory gradually shaped by the gravitational influences of stars it passes near over millions and billions of years. It will drift through the galaxy as the galaxy itself evolves, long after the sun has exhausted its fuel and the Earth has ceased to exist in its current form. The golden record it carries will survive, barring a collision, for billions of years. A physical remnant of a civilization that will itself have changed beyond recognition or ceased to exist entirely. What Voyager ultimately represents, in the very longest view, is a message sent, not to any specific recipient, but to time itself, a small and quiet testament to the fact that once, on a pale blue dot orbiting an ordinary star, something became curious enough to reach outward into the dark,